So recording progress. So please, Thomas.
Okay, so well, this is we're just crossing the equator of this course. So today I'm going to tell you about numerical methods, simulation methods to simulate all these things, because, well, as we mentioned during the two previous lectures, analytical solutions, or even the sort of approximate solutions that we were looking at the other day using WKB-like methods, are not always available. In fact, they are very rarely available. So most of the times, one has to resort to numerical methods. Okay, so and this is what I'm going to tell you about. So I will start by explaining this Gillespie stochastic simulation algorithm, which is my favorite numerical method in the world, and I think it's a very nice method, and it has some rather unique features. And then we will go to my least numerical method in the world, but this is one thing that a lot of people applies. So I will also tell you about it yeah. So before I start with this, are there any questions regarding the previous lectures that?
Yeah, can you still send us the slides, because it's good to.
Sorry, say again.
The slides of the previous lecture.
You want? Oh, okay. I didn't send it to you. Yes. It will happen. Okay, don't worry. Okay, so if there are no more questions or petitions, I will proceed. Okay, so well, as we were saying, sort of analytical or asymptotic solutions to this kind of systems are rarely available. So most of the times, to study the systems, we need to resort to numerical algorithms, stochastic Monte Carlo simulation methods. Okay, and the most basic algorithm is this so-called Gillespie algorithm that was proposed by Dan Gillespie in this paper in Journal of Computational Physics in '76. So this is a rather old paper, but it's a very interesting one. In fact, I do recommend that people get this paper and have it, because it's really an interesting paper, on not just on the algorithm, but on the sort of physical interpretation of these processes, and it's really an interesting paper. So if someone has difficulties getting it, just drop me an email and I will send you a PDF. Okay. So basically, this algorithm, and the one that I'm going to tell you about later, the Talib method, what they generate is sample paths or realizations of the Markov process. Okay, and the statistical properties of the ensemble of such paths, when we take, of course, the number of paths going to infinity, these statistics converge to the solution of the corresponding master equation. Okay, so in this sense, we always say that this is an exact algorithm. Okay, because you are sampling the solution of the master equation, the exact solution of the master equation. Okay, so in this sense, this is why I was saying before that this is a very peculiar numerical algorithm, because it converges always. Well, provided that you have coded up correctly, it always converges. There is no issues like you have in, for example, when you do numerics of PDEs, that you always have problems, and sometimes you have problems of convergence. I mean, this converges unconditionally, and you are always sampling the exact solution of the master equation. Okay, so this is this is why this is a very good algorithm to benchmark things. Okay, so when you as we will see, it's a very good algorithm, but it can become inefficient from the numerical point of view or from the computational point of view. It requires a lot of time, a lot of computation time, and then you need to formulate alternatives. But this is a very good thing to have as a benchmark, because it's kind of the true solution of the master equation. Okay, or you are sampling the true solution of the master equation. Okay, so this is what I was saying. The algorithm is based on an exact representation of the master equation. Okay, sort of the mathematical foundation for the algorithm is based on a reinterpretation of the master equation, where we try to find an expression for this quantity here, which we call the elementary process probability. Okay, so this is the central quantity of the method. Okay, so recall that this quantity here, the rate multiplied by the this delta t, is the probability of this event I, so the event that has associated this rate, to occur between t and t plus delta t. Okay. Now, this quantity that we were mentioning before, this elementary process probability, is such that this quantity times delta t is the probability that the next process to occur in this time interval is process I. Okay, so basically what we are looking at is we have the state, we are looking at the state of the system at time t. Okay, and then we look to time units into the future. Okay, and we want to know the probability that the next event to occur occurs after a time tau has elapsed. Okay, so this is very much, as we will see, this is very much related with the waiting time probability. Okay, so basically what we are asking here is, what is the waiting time probability, the time that we need to wait for the system to undergo some sort of transition. Okay. Now, this quantity here can be written as the product of the probability that nothing occurs in this time interval. Okay, and we call this P naught of tau, and the probability that the event I occurs between t plus tau and t plus tau plus delta t. Okay, so this is given by this quantity here. No complaints? Nobody sees anything strange here?
Is tau, so it's just in the period tau, it's not related to the time t, isn't it?
Okay, yes, but that's exactly very well, Stefanella. But the point is that we are conditioning to nothing happen in this time interval. Okay, so at time we are looking at the probability that something occurs within this time interval here. Okay, so this implies that nothing has occurred between t and t plus tau. So we are so the state of the system at time t plus tau is still x of t. Okay, because we are conditioning to nothing happening between t and t plus tau. Okay, and this is why we can write this in this way. Okay, now obviously if we want to derive this, so basically then because of the Markov property, we can write this quantity in this way as the product of this P naught, the probability that nothing has happened between t and t plus tau, and the probability that whatever that occurs within t plus tau plus and t plus tau plus delta t. Okay, this is the, and because it is a Markov process, we can write this as a product. Okay, so now the next step in the derivation is, of course, calculating this P naught of t, of tau, sorry. Okay, and to do this, we first divide this time interval into k equal intervals of duration given by epsilon equal to tau divided by k. Okay, so this we are going to take this as a sort of a large partition. Okay, so we partition this interval in k subintervals of equal duration. Okay, now this is the probability that nothing has happened between t and t plus tau. Okay, so the probability of no reaction occurring during any of these subintervals, okay, is 1 minus the, so the probability of something occurring, of event I occurring within this subinterval is given by the product of the W of the corresponding W multiplied by epsilon plus things that are of order epsilon squared. Okay, so this is the probability that reaction I occurs in this subinterval. Okay, so the probability of not of the reaction not occurring in this time interval is 1 minus this quantity here. Okay, and because we are assuming that all the different reactions occur in a statistically independent way, the probability that nothing has occurred during this time interval epsilon is the product of all these probabilities. Okay, and because we are assuming that k is very big and therefore epsilon is very small, so we can rewrite, or we can approximate this this product as 1 minus this sum plus things that are of order epsilon squared. Okay, now we use the Markov.
Sorry, I have a question. I didn't understand exactly the term of a higher order of epsilon squared.
Yes, this is, well, this is because well, here or here?
In the first place.
Okay.
Yeah.
So
Yeah.
okay, so let's imagine that we have a parenthesis here. Okay, so what I'm saying is that the probability, so we are looking, so these W quantities are the rate of probability. So it's the probability per unit time of event I. Okay,
Yeah.
so
Yeah.
if you have a very small interval, so if you are considering a small interval, okay, the W multiplied by the small interval is going to give you approximately the probability of the event occurring, but that has corrections. Okay.
Okay.
And those corrections are order epsilon squared.
Okay, I understand now. Thank you.
That's just because the definition of the W is a rate. Okay, so that's why you have this thing here.
Yeah. Thank you.
Okay. So now so again, the probability of nothing happening during one of these subintervals is therefore given by this thing here. Okay. Now, using the Markov property, okay, we can write now this P naught of tau, the probability that nothing happens during the whole interval, as the product of the probability of nothing happen in during each one of the intervals, of the subintervals. Okay, therefore we will have this expression. Okay, here we have used that epsilon is tau divided by k. Okay, and again we have contributions here of order k to the -2. Okay, and now this thing here, because we are assuming that k is much bigger than 1, if we let k go into infinity, this is going to be familiar to everyone as the definition of the exponential. Okay, in this limit, we have that p naught of tau is equal to this quantity here. Okay, so this is here just applying the definition of the exponential. Is this clear? Because this is basically the whole thing with the algorithm. Okay, and again, I mean, we can here, as we pointed out before, we are during the whole interval we are keeping this x of t here. So here we don't have x of t plus whatever. We have here x of t because we are conditioning to nothing happening within that time interval. Okay, so this means that the state of the system is still the same state as we had at time t. Okay, so with this, okay, we have that this probability, okay, which I recall that which we remind that it's the probability that the next event occurs after a time tau in an infinitesimal interval of length delta t, okay, is given by this combination. So basically, what we have used is using this this definition here, okay, and now we use the p of tau, okay, and yeah. So this thing can be rewritten. So this quantity here, this p of tau I, can be rewritten in this way. Okay, so this is the probability that condition to the state of the system at time t, the waiting time is tau, and then the probability that condition to the state of the system at time t and condition to the waiting time to be tau, this is the probability that the next event to occur is event I. Okay, and we can rewrite this in this way. Okay, so to see this, it's very easy. You just have to multiply and divide this expression by this term here. Okay, and this will give you the sort of normalized probability for the waiting time conditioned to the state of the system at time t. Okay, so again, this is the waiting time distribution conditioned to the state at time t to be x of t. Okay, and here we see that this is an exponential distribution. Okay, so this is what we were saying at the beginning of the lectures, that the Markov property is very much related to the fact that the waiting times between events are exponentially distributed. Okay, so here we see this explicitly. Okay, by reformulating the master equation in this particular way, we can see that by means of the Markov property, which is the one that allows us to write this quantity in this way, we can deduce that the waiting time distribution is going to be an exponential. Okay. Yeah.
Thomas, one second.
Yes.
So the difference between the probability tau e and the conditional probability, how between the two expressions
No, you can. This is okay. Let's go back here. Okay, so now you have this expression. Okay, and now you multiply this expression and divide by the sum, by this sum here.
Yes. Okay. Yes.
Okay, and then you group and then you group factors. Okay.
Okay. Okay.
So see, and then you will see that you can write it in this way. Okay.
Okay.
This is the normal, because the problem with this thing is that this is not normalized to 1. Okay.
Yes.
So that's we are calling this a probability, but we shouldn't. Okay, because that's not normalized. Okay, but by writing it in this way, this is a proper probability now, because this is if you integrate tau from 0 to plus infinity, this is giving you 1.
Yes.
Okay, so so this is why we do this. Okay, just to write this as the product of two things that are probabilities.
Okay, thank you.
So now this exactly. So this is the waiting time distribution. So you are sitting at time t, your state is x of t, and then you see, okay, when it's going to until when I have to wait for the system to change its state. Okay, and this is generated by this exponential distribution. Okay, now once you have waited the time that you have to wait, and that's prescribed by sampling this probability distribution, you have to choose which of the possible things that can happen to your system is going to happen. Okay, and the probability and this p of I conditioned to these two things is telling you which one of the processes that can affect the state of your system is going to happen. Okay, so for example, if you recall the examples that we looked at in the first lecture, where we were looking at birth and death. Okay, so there you had only two events that could affect the state of your system: birth, that adds one individual to your population, and death, which removes one individual from your population. Okay, so in that case, I could be either 1 or 2. Okay, birth or death. Okay, and the probability that a birth happens is the rate of birth divided by the sum of the birth plus the death rate. Okay, and again, you can see that if you add this over all the possible values of I, this is giving you something that is normalized to 1. Okay, so in this way, so what we have done by sort of rewriting the master equation in this way is we have transformed the master equation into a continuous time jump process. Okay, so at each time there is the state of the system, then you have to wait for a given sort of waiting time for the next event to happen, and that's prescribed by the waiting time distribution. And then the system, once you have waited for that time just that you obtain by sampling the waiting time distribution, you choose in which way you are going to change the state of the system. Okay, and that is also done probabilistically, and the probability that the process I changes the state of the system is given by this probability here. Okay, so for example, in the case of the birth and death process, if you have that the probability of birth is 99 and the probability of death is 1, you are going to have a 99% of probability of choosing birth and a 1% probability of choosing death. Okay. So, and that's basically it. It's not. It's very simple. So I will now go through the algorithm just to. So basically, just to recapitulate, so the way the algorithm works is that you initialize your system, so give some initial condition at time 0, and you initialize the seed for your random number generator. Okay. So now at each time step, what you do is you calculate all the rates. Okay. And then you calculate this quantity W naught, which is simply the sum of all the rates in your system. Okay. Now the next step is that you generate 2 random numbers from your favorite random number generator. Okay. So this will be uniformly distributed in the unit interval. Okay. And then you calculate the waiting time in this way. So this is the way of sampling an exponential distribution. Okay. Or you just if you, for example, if you're using MATLAB, you can just use the whatever sampling algorithm they have to sample the exponential distribution. Okay, but you can just program it directly using this formula. Okay, and then so you calculate the waiting time, and then you calculate which process occurs by choosing which process is going to occur in this way. Okay, so this is the way of sampling this probability distribution. Okay, so is this clear to everyone or not?
So why can you just go over this last?
Okay, yes. So basically, so this thing here, okay. So P of I is going to partition. So P of I has to be between 0 and 1 for each I. Okay. So basically, what this is going to give you is a partition of the unit interval. Okay, where the length of each partition corresponds to the weight of each one of the events that it's going to occur. Okay, so imagine that again you have a birth and death process. Okay, and you assign the number 1 to birth, number 2 to death. Okay, so in that case you are going to have the interval partitioned into subintervals. Okay, and what you are doing when you are generating set 2, which is random, which is uniformly distributed between 0 and 1. Okay, you are going to just say, okay, so I'm going to fall. So you are going to generate that random number between 0 and 1, and then you can fall in one subinterval corresponding to death, or one subinterval, or the other subinterval corresponding to birth. Okay, and because the number that you are generating is randomly distributed, the length of the intervals is going to be the probability that one thing or the other happens. Okay, so when you do this for an arbitrary number R, what you are doing is this. Okay, so this omega 0, you can, if you move this omega 0 dividing over here and over here, what you say is that this is the probability. So what you are looking is when what is the probability that this random number set 2 falls into one of the intervals corresponding to having chosen J. Okay, in general you are going to have more than 2, but it's the same idea. Okay, and this is how you sample this sort of distributions. Is that clearer now?
Yes, yes.
Okay, so now here you have with this you have tau. Now you have J, and then you can just update the state of the system. Okay, so you update T to be T plus tau, okay, which is this random number here, and then you update the system so that x of t plus tau is whatever xt was plus the change in the state of the system associated with the process that has been chosen by the Gillespie algorithm. Okay, and then basically you iterate steps 2, 3, 4, 5, and 6 until some stopping criterion is fulfilled. So you can have something like t bigger than some prescribed time or whatever. Okay, so now this is going to generate a sample path. Okay, if you want to extract useful information from that, you have to generate many of these paths and then do a statistics over this. Okay, is that clear? Okay, this is an example that I think we saw in the first lecture, illustrating that well, the effect of noise when you have different current capacities. Okay, so questions, complaints?
No, the say is clear.
No complaints. Okay, so so I'm going to give you the motivation for you to stay for another 40 minutes, and then perhaps we can do a 5-minute break. Okay, so now the SSA, as I said, it's my favorite numerical method in the world, but it has a very serious drawback, and it's poor computational performance. Okay, and this is, and you can imagine why this is so, because what we have seen is that this algorithm, what it's doing is recapitulating the whole dynamics of the system event by event. Okay, so you have to, it's like watching a movie, but photogram by photogram. Instead of watching the movie moving, you just see the moving, something like clack, clack, clack. And of course, when you have a lot of reactions, or you have big system size, or you have a slow and fast process that need to be considered in the same model, which is something that is very common in very slow. Okay, so slow that in many, oops, can you hear me? It's saying that my
yes,
internet
we lost you for some seconds,
okay.
but you're back.
Yes, sorry, I'm at home and I'm connected with a telephone. It's not particularly stable. Okay, so what I was saying is that this can become very computationally intensive. Okay, because you are recapitulating the dynamics of the system event by event. Okay, so it's like a very slow thing. Okay, so this means that sometimes in some systems, in some types of systems, particularly when you are trying to do reaction diffusion systems or things like that that require spatial sort of resolution, this can become very computationally intensive, and in fact it can become impractical. Okay, so you need to resort to less nice numerical methods, but that are more efficient numerically. Okay, so in the case of so basically we need to resort to methods like this Talib method that I'm going to tell you about next, where accuracy is traded off somehow in the benefit of performance. Okay, and well, sometimes this is okay. So the difference between the Talib method and the Gillespie method, the SSA method, is that Whereas in the Gillespie method, you sort of generate event by event by generating the waiting, the time that you have to wait until the next event. What we are going to do, or what the Talib method suggests, is that we fixed a time step somehow, and the way in which we select the time step is basically the method. The meat of the method is basically selected this time step, and then we estimate the number of times that each of the events has occurred. Okay, so it's a different point of view. Okay, and yeah, so I guess that we can take now a 5 minutes break.
Yes. Yes.
And then we're going to start with the math. Okay. Good.
Thank you. 5 minutes.
Thank you.
So you can start again.
Okay, good. So yeah, well, the first step in the derivation of the method, of the Talib method, is basically rewriting or represent the process, the stochastic process, in this way. Okay, so now this is actually equivalent to the master equation in the following sense. Okay, so here we have x at time t. We write it at x at time 0, like x naught, plus this sum here. Okay, and this each of these quantities here, this set I, is what it's called the advancement coordinate for the process I, for each one of the processes, which means that it's the number of times that process I has occurred in the time interval 0t. Okay, so basically what we are saying here, what we are looking at here is, imagine that the system is again a birth and death process. So this R is equal to 2, and 1 is birth and 2 is death. Okay, so now what we are doing is writing the system in the following way. So at time t, the number of individuals in the system would be the number of individuals at time 0 plus the number of births multiplied by +1. Okay, because every time there is a birth event, the size of the system is increased by 1. Okay, plus the number of deaths multiplied by -1. Okay, and that would give us the population at time t. Is that clear?
Yeah. Yes.
Okay, good.
So but this ZI, how is estimated by simulation? How do?
No. It's I will get there in the next.
Okay. Okay.
I will get there very soon. Okay. So similarly, okay, we can write the state of the system at t plus tau. Okay, like as the number of individuals at time t plus this thing where now set of I tau is the number of times that the process I has occurred at time tau. Okay, now because we know that the system is Markov and the waiting time between events is exponentially distributed, this set sub I here is distributed according to a Poisson distribution. Okay, that's because we know it's a result. It's a very well-known result in probability theory that if you have a system with a waiting time that it's exponentially distributed, okay, and you count, you fix some sort of a time interval, and you count how many events have occurred in that time interval, that's going to be given by a Poisson distribution. Okay. Now, because we know that the process is a Markov, it's a Markov process, and the waiting time distribution is an exponential one with a parameter that is given by this thing here. Okay. Then set I is distributed in this way. It's a Poisson distribution with a parameter that depends on time. Okay, it's not a constant parameter. It's something that depends on the state of the system. So that we have that this is like this. Okay. So now we are just to make it explicit that this Poisson distribution depends on something that it's depending on time. We are going to use this notation here. Okay, so we can write this equation by just in this way. Okay. Now this is, as it is, completely useless. Okay, because this lambda I of tau, of course, depends on the whole history of the system. Okay, so we cannot. So this equation is exact, but it's useless from a practical point of view. Okay, but if tau is small, this integral here that gives us this lambda I can be approximated in this way. Okay, this is a very, very rough approximation, but if tau is small and this W functions satisfy some conditions, it should be a reasonably good approximation. Okay, so that from these two equations here, we obtain the Talib formula. Okay, which is this. So here, if we assume that we know tau, we know everything, because we know x of t, therefore we can sample this. If we fix the tau somehow, we can sample this from here, okay, from the Poisson distribution, and therefore we can give an estimate of the state of the system at time t plus tau. Okay, so now the trick here is that I haven't told you how to see it, this tau, so this could work. Okay, so and this is kind of the meat of the method. Okay, the first thing is that the Talib method somehow converges to the Gillespie SSA algorithm if you choose a tau that it's very small. Okay, so if you choose a tau so that it's very small, then you're probably not gaining very much by doing this. Okay, this thing here that we have called the Talib formula, or rather Daniel Gillespie called the Talib formula. Okay, so for this formula to be a good approximation, both tau and the rates must be such that the propensity functions will not suffer what Gillespie called an appreciable change when x moves from x of t to x plus tau. So okay, so this basically means that that the quantity here, the change in the variable x, needs to satisfy some conditions. Okay, so this statement, which we will make more precise in a minute, is the so-called Lip condition. Okay, so this condition that this function must be such that the propensity functions, so these things here, will not suffer an appreciable change, when we move. Basically, what means is that we need to make sense of this approximation. Okay, so this is basically what we are going to try to do. Okay, we need to make sure that this approximation is not a terrible one. Okay, and the third thing is that if tau is not chosen properly, then the Talib formula can give you some sort of artifacts. For example, if you're studying one of these birth and death processes and somehow you overestimate the number of deaths, you can end up with a negative population, which is sort of an unphysical result. Okay, so these three things need to be taken into account when we sort of formulate the algorithm for choosing tau, okay, which is what we are going to see now, and also when we do the implementation, we need to put some sort of flags or something just to make sure that we are not in this region here where the method is useless, or that these things cannot happen. Okay. So now we go back to the leap condition, okay, which is basically the conditions under which we can make this approximation. Okay. So by the way, I forgot to mention this. This Talib method was also proposed by Gillespie as a sort of improvement in the efficiency of his original algorithm. And well, it has been, there are many versions of this system. Okay, so basically what we are going to see now is basically a prescription for choosing tau. Okay, and this is a prescription. This is not a theorem, or it's not a sort of, it's not that there is not a theorem for choosing tau. Okay, so these are prescriptions, and there are many prescriptions of this type. Okay, so what I'm going to do is I'm going to show you the original one by Gillespie, but this prescription has been improved in other methods. So for example, you can look at the, if you are curious about this, you can look at the work of Linda Petzold, who has worked a lot on this sort of improving these leap conditions. Okay, so again, I mean, we need to, this sort of caveats tell us that we need to choose tau in a proper way. This is sort of critical for the method to work. And again, there are several methods in the literature. Okay, so but this is what I just said. Okay, so now, first of all, recall that we are approximating this advancement coordinate by a Poisson probability with parameter lambda equal to Wi multiplied by tau. Okay, so now what we want to do is, in order to keep this approximation under control, we need to make sure that the change in the variable is not very big. Okay, we need to control the change, otherwise this approximation is not going to be good. Okay, so we need to control both the change in the state variable, in the value of the stochastic process, and also we need to check that this that the WAI quantities do not sort of explode. Okay, so this is what we are going to do. Okay, so now the expected net change of the state of the system in the chosen tau interval, okay, is which is the average, this average here. So by the way, I don't know, are you familiar with this notation? This is the notation that the physicists use for the average. Okay, so whenever you see something between these two parentheses, okay, this means average. Okay, so the average in the net change of the state of the system is given by this quantity here. Okay, so basically what we do is we go back here. Okay, so the change in the state of the system would be x of t plus tau minus x of t. Okay, so that would be our delta x, and we take the average over of that quantity. Okay, and what we get is this. Okay. Now, so we can write it in this way because we are assuming that all these quantities are independent from each other. Okay, so yi is independent from yj. Okay, so then we can write the average in this way. Okay, and because these yi's are a Poisson variable, the average is given by this quantity here. Okay, so the average of the Poisson distribution with a parameter lambda given by this quantity here is just the parameter lambda. So wi multiplied by tau. Okay, and now we take tau common factor out of the summatory, and we can write this in this way. Okay, so where this quantity psi of psi, which is basically this quantity here without the tau, is the average expected state change per unit time. Okay, so that's kind of a rate. Okay, now the leap condition can be stated in this way. Okay, so we want, sorry, this parenthesis here should be, this should be an I, and there should be a parenthesis here. I apologize for this. Okay, so basically what we want is that the change, or what we require is that the change in the W function when the system changes in this quantity stays bounded. Okay, and the way in which Gillespie choose to do this bounding is by saying, okay, the increment in the Wi rate has to be smaller or equal than some function epsilon I of xt. Okay, so so this criterion, Gillespie's criterion, consists of, first of all, considering that this bound here, that in principle depends on I, is now something that doesn't depend on I. So the bound is the same for all the rates. Okay, and then it's bounded by this W0, which corresponds to the sum we defined that before. Okay, so basically the variation in x of t is of the order of the average, and the variation of the propensities, which is that of the W functions, are all bound by the inverse of the average waiting time. Okay. So by assuming that, recall that we have now said, okay, we are going to assume now that the change in all the variables is basically of the same order, that the variation of xt is of the same order of the average. Okay, so this is basically this formula here. Okay, and we are going to see, we are going to take this and see where we go. Okay, also we assume that the average change is smaller than or much smaller actually than the actual value of the variable. Okay, and in this case, basically what we can do, we can take this thing here, use this formula here. So x of t plus tau is equal to x of t, or approximately equal to x of t plus the average value of the net change in the variable. Okay, and by using this, we can Taylor expand this thing, and if we stay at first order, this is what we get. Okay, This is just doing the Taylor expansion of this thing. Okay, then the first term will cancel, and we only keep order delta t delta or order delta x terms. Okay, because we are using this now. Using the calculation that we did before, this delta x can be substituted by this thing here. Okay, and therefore, using the Talib condition, this is what we obtain. Okay, and the Gillespie's lib condition is that we take the minimum of all this, the minimum of this. So this still depends on I. So we pass this to the other side, and we choose tau, so that this is the minimum. Okay, and this is how we choose tau. Okay, so at each time step we need to use this formula, okay, to determine x. And the not so nice a thing about this method is that you have here a free parameter. This epsilon 0 is something that you have to fix by hand. Okay. So this is not a way of how to fix this this epsilon 0 is not provided by the method. Okay. There has been recent work into try to combine this with optimization techniques in order to obtain some sort of estimation of what epsilon 0 should be, but that's sort of beyond our scope. Okay, and again, the Talib algorithm, okay, is again we initialize the system, initialize the seed for the random number generator, and we fix the value of this epsilon 0. Okay. Then again, just like in the Gillespie algorithm, we calculate the W quantities, we calculate the W naught quantities, and then we calculate tau according to the lib condition, which is this formula here. Okay. We generate sorry, R. This should be an R. Are random Poisson distributed numbers using this a Poisson distribution with this parameter here, because now we already have tau, so we can sample this distribution. Okay, and then we update the system according to the Talib formula, which is this one here. Okay, so now here we know everything because this is part of the model. This is part of the model, so we have calculated using the method. So we can sample these WI quantities, and we can apply this formula to update the state of the system. Okay, and then we update the time. So basically, just as in the Gillespie algorithm, we update it by tau, and again we iterate the steps 2, 3, 4, 5, and 6 until some stopping criterion is fulfilled. Okay, and that's it. I mean, this is several examples that, well, no, it's actually an example. Yeah, it's a couple of examples that Gillespie proposed in his paper. And we can see here that, well, comparing with the exact SSA model, sorry, method, I mean, the comparison is okay, you know. And whether you have whether we have done 2000 steps No, sorry, this is, yeah. Sorry, this is the Talib solution. Okay, so there is no approximation here. Okay, but note that the number of steps, so it's over 500,000 number of steps, whereas with the Talib method with an epsilon of value 0.03, you only have to do 400, a little under 500 time steps, and you get a solution that it's very much an approximation to the real system. Okay, and that's it. So again, I mean, this Talib method works well, but particularly fixing this value requires a bit of tweaking, and it sometimes requires even try to run the stochastic simulation algorithm in some case where you know that you can do the stochastic simulation algorithm, the stochastic simulation algorithm simulations in order to get some sort of comparison. So the problem with this algorithm is basically this parameter here, that you need to do quite a bit of tweaking regarding that. So in fact, and as I said, this is a sort of an active field of research, how to when you are using these Talib methods or methods that are similar, how to parameterize them so that you don't have to run Gillespie algorithms to just compare or something like that. Okay, and this is I think everything that I have to tell you for today. So next week I'm going to be a bit cheeky here because
Thursday.
Huh?
Thursday, not next week.
Oh, sorry. Yeah, next lecture. Sorry, Thursday. Yeah, sorry. I'm going to be a bit cheeky, and I'm going to talk a little bit about my own research. So I'm going to show you an example that I think Stefanella will like, because it's about HIV, some modeling that we did a few years ago, and just to give a flavor of how all this can be applied and how all this works in a sort of real research sort of a scenario. Okay, so if I'm allowed
Great.
to be a bit cheeky,
yes,
then
yes, of course. We want to hear about your research.
Good. So we still have some time, I think. So if someone has questions, I'm quite happy to answer.
Question. Do not be shy. Don't be shy.
Where's the chat?
But first of all, let's thank Thomas again for this marathon. Thank you so much. So let's thank you that opened the microphone to thank. Please join me to thank him. So, question. Let me see if someone from YouTube. No shy, all shy. 1 second. Question I ask here. There are people on YouTube question.
Okay, so perhaps next time people will be less shy, and
Yes.
and they will have a last opportunity.
And the last option before. But okay, in the meantime, send us the slides, because so it's good. People can look back and can think. No, yeah. Now students want the slides, the video, the material. It's not like our old day that you have to take notes, you know. Yeah. Everything has to be.
Well, I usually do this course on the Blackboard. So
Yeah. The famous interaction.
yeah, but, yeah,
The whole time. Then let's go back. Let's hope that we go back in person one of these times.
I would have loved to go to Rio to do this.
Oh yeah. We can organize. We can organize to import you. We can. Yeah, when there are no bans between the country, we can organize. We did took, for example, a very good period to import people is during our summer program. That is January and February, because we have extra money for that to import visitors. So one year I imported 2 from the States. And so yes, Rafael Meza, I don't know if you know Rafael Meza. Yeah, we import.
No, not personally, but yeah, I've heard.
Yeah. So that is a good time too. But this year it's still like it's a little bit strange about if we can import visitors.
It's not going to work now.
Yeah, but next,
okay,
maybe 2023, who knows? Okay, so thank you very much.
If nobody has questions, perhaps we can just.
Yeah. Okay, so we like to go to have dinner, and thank you once more for a great lecture. And and so we look for the slides, so people maybe can look back and have notes, questions.
I will send. I promise.
And yes, and the article that you mentioned from Gillespie, it would be nice to have it.
Which article?
The one from Gillespie, the one
the
the first, the Gillespie, the one of the first method. They say that it's inspiring as in general to read. So
it is very nice. I mean, particularly if you're interested in the physical motivation of all these things like the law of mass action and the sort of hypothesis that you have to do for that to work.
Yeah.
I think it's a very interesting one.
Yeah, so
I will send you the PDF.
Okay. Thank you very much, Thomas. Bye-bye. Have a nice dinner. Bye-bye. See you Thursday. Bye.